Hello everyone, my name is Jonathan and today I'll be presenting my final year project on real estate app development and recommendation system. The e-commerce market has grown tremendously over the years, leading to a heightened need for social recommendation algorithms that can assist buyers in selecting the best properties based on their needs and preferences. Our project involved reviewing existing commercial solutions in a real estate recommendation, analyzing their methodologies, approaches, and challenges. Through this analysis, we were able to identify the gaps in current models and develop a social recommendation app that utilizes a multimodal algorithm to circumvent these challenges. To evaluate the effectiveness of our proposed algorithm, we use both public and proprietary datasets. We believe that our research contributes significantly to the development of the effective real estate recommendation algorithms that can enhance user experience in property acquisition. Our app aims to make the property acquisition process easier and more enjoyable for buyers by providing them with personalized recommendations based on their needs and preferences. Existing solutions include user-based collaborative filtering, which is an approach that recommends items based on what similar users have previously shown interest in. In the property market, this approach can help identify properties that other similar buyers are deciding to purchase or are showing interest in. An example of user-based collaborative filtering in the property market is housing recommendation system, previously used in Beijing, which recommended properties to users based on browsing rental records, leading to higher user satisfaction. Another example is item-based collaborative filtering, which recommends similar items based on what the target user has previously liked, making it useful for the property market for recommending properties with similar characteristics. Hao Kai Lu developed a property recommendation system using item-based collaborative filtering that predicts users' preferences based on browsing history, transaction records, and property similarities. This approach was evaluated using cross-validation and outperformed other techniques in recommendation accuracy. In the property market, different recommendation models such as item or user-based collaborative filtering have been used with varying success. However, in our use case, we faced a lack of historic users rating data. Therefore, we propose a hybrid collaborative filtering model that combines matrix factorization and item-based collaborative filtering to address issues such as our code start problem. By leveraging the strengths of multiple models, our implementation aims to navigate the complexities of the current property market and provide a more accurate and personalized property recommendations. We combine various data sources to gather each property's characteristics for every property type. Due to insufficient public data, we decided to narrow our scope and only utilize property data for which transactions have already been recorded. We also utilize current market data provided by PropNext. Next, we pre-process our data by changing the data types to our use case, scaled and normalized data. We use truncated SVD to reduce the feature matrix dimensionality. Matrix factorization is a technique that breaks down a large matrix into smaller matrices to simplify computation and extract meaningful relationships between items and users in a recommendation system. The hybrid SVD cosine similarity function utilizes pre-processing, truncated SVD, and cosine similarity to identify the top 3 most similar properties. Cosine similarity measures the angle between two vectors in a multi-dimensional space. The model takes use of this to calculate the pairwise cosine similarity between the given project and all other projects within the reduced feature matrix. The function takes about 10.95 seconds to complete with the following predictions. Similarly, the hybrid SVD KNN clustering function utilizes pre-processing and truncated SVD. However, it uses the k-nearest neighbors algorithm to identify the k most similar properties to a given property. The similarity is measured using Euclidean distance, and the algorithm can be implemented using different search techniques such as ball tree, KD tree, and brute force. KD tree was the fastest performing k-nearest neighbor algorithm, taking only 2.5 seconds to complete the process while still recommending the same results as the other two k-nearest neighbors algorithms. The comparison between hybrid SVD cosine similarity and hybrid SVD KNN clustering models showed that the KNN model is much more efficient in terms of execution time. Although both models provided different sets of recommendations, the properties recommended by the cosine similarity model appeared to have features closer to the input property. This is because the cosine similarity model focuses on similarities of relative feature patterns, resulting in recommendations with closer sale prices and similar floor and area values. On the other hand, k-nearest neighbor models considers mostly relative characteristics as well as actual values of the features, leading to recommendations with much more diverse feature values. While cosine similarity model takes longer to run, it's a much more optimal and balanced model for our dataset. To evaluate the performance of our recommendation system, traditional metrics such as classification accuracy or F1 score are not applicable as we are not predicting a class label. Instead, we use evaluation metrics such as MAP at K, MRR, or hit rate to measure the quality of our recommendations. As we lack user interaction data and ground truth data, we cannot test this evaluation yet. However, we have implemented these functions so that once we have sufficient user interaction data, we can use them to improve the accuracy of our recommendations. MAP at K is an evaluation matrix that computes the average position scores at different positions where relative items are found at the top of the list up to position K. Precision is the proportion of relevant items among the top K recommended items. MAP at K also takes into account the order of the recommended items and the relevance of the items at each position in the list. MRR is an evaluation metric that measures the ability of a recommendation system to present the most relevant items at the top of the list. It calculates the average of the reciprocal ranks of the first relevant item in the list of recommendations, and is very useful when users are only interested in the top recommendation, which puts more emphasis on getting the first relevant item right and less sensitive to the order of the items beyond the first relevant item. Lastly, hit rate is used in situations where recommendation systems are using binary recommendations, such as recommending whether a property is liked by a user or disliked. In this case, a hit is recorded when the recommended property is relevant to the user, and a miss is recorded if it is not. This metric is simple to calculate and provides a straightforward measure of performance. Our project developed the PropNext Investment Suite, a social recommendation cross-platform app for the real estate market. Public property data was sourced, crawled, and integrated into a cloud database, and multiple recommendation models were tested. The combination of truncated SVD and cosine similarity was found to be the most effective and provided the most well-balanced results. Our project contributed to the property recommendation systems research, addressing the need for accurate, personalized recommendations in a competitive real estate market, and paved the way for more sophisticated and user-centric applications. Thank you for watching, and we hope that our research can inspire further developments in the field of real estate recommendation algorithms.